Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Aina Shahzuna binti Sahidan and I will start with introduction. Distributed computing system are widely used in modern application because they provide a better scalability, reliability and performance compared to traditional centralized system. In a centralized system, all client requests are handled by a single server, which can lead to problems such as server overload, slow response time, and also single point of failure when many users access the system simultaneously. To overcome this limitation, system distributed system distribute workloads across multiple servers and nodes to improve communication efficiency and system availability. This project is based on a university communication scenario where student and lecturer use an online messaging platform for discussion, announcement, and also academic collaboration. During peak periods, such as assignment submission or online classes, a centralized communication system may experience high traffic loads that can cause delayed message delivery and server congestion. Therefore, the purpose distribute chat system use multiple server and replication mechanism to distribute workloads efficiently and maintain performance.
The objective of this project are: first, to develop a distributed communication and assignment submission system for student and lecturer in a university environment. Second, to implement multi-threading technique to support multiple users accessing the system simultaneously during peak periods. Third, to develop a naming system for user identification and efficient message routing between student and lecturer. Fourth, to implement data replication and consistency mechanism to improve reliability and fault tolerance. For the last, to analyze the performance and scalability of the system under high traffic conditions such as assignment submission periods. This slide presents the architecture of our university communication system. The system is designed using distributed computing concept to support communication between student and lecturer in a reliable and efficient manner. As shown in the diagram, the architecture consists of 5 main components. First, the client process represents connected user and handle communication requests. Second, the naming system identifies user and determines the correct server for communication. Third, replica server maintains synchronized copies of data to improve availability and fault tolerance. Fourth, the sequential consistency server ensures that all updates are applied in the correct order. Finally, the shared resource store common data that can be accessed by multiple threads while maintaining consistency through synchronization mechanism. Together, these components available efficient communication, reliable data management, and support for multiple users operating simultaneously. This slide explains how communication takes place within the system. First, a user sends a communication request through the client process. The naming system then identifies the destination user and determines the appropriate server. The request is processed concurrently using multi-threading, allowing multiple users to communicate at the same time. After that, replica servers synchronize the updated information across distributed servers to ensure consistency and availability. The sequential consistency server that guarantee that updates are applied in the correct sequence, preventing conflict and maintaining data integrity. In terms of scalability, the architecture allows additional user and server to be added easily as system demand grows. For fault tolerance, replicated servers provide backup support, ensure that the system continues operating even if one server becomes unavailable. Overall, This architecture provides efficient communication, reliable data synchronization, strong fault tolerance, and scalability for a university communication environment. This slide explains the process management approach used in our university communication system. Since many students and lecturers may access the platform at the same time, efficient process management is required to maintain good performance and reduce communication delay. The system uses multi-threading, where each user connection is represented as an independent thread. For example, users such as Aina, Dr. Shu, and Maisara are executed as separate threads and can communicate simultaneously. The start method allows all threads to run concurrently without waiting for one another. As a result, the system can process multiple communication requests at the same time. This approach improves communication speed, utilizes system resources more effectively, and provides better scalability when the number of users increases. This slide focuses on synchronization and system evaluation. In a multi-threaded environment, multiple threads may access the same shared resource at the same time. In our system, the shared variable message count is protected using the synchronized keyword. This prevents race condition and ensures that the data remain accurate and consistent. The project also compares thread-based and process-based execution. Thread-based execution is more suitable because it requires less memory, provides faster communication, and supports better scalability. Since threads share memory, they can exchange information more efficiently than separate processes. To evaluate performance, high concurrency simulations were conducted by creating additional user threads. The results show that the system can support multiple users simultaneously while maintaining accurate message count and stable performance. Although synchronization introduces some overhead and increased complexity, it is necessary to ensure reliable communication and consistent system behavior.
Next is naming. The naming system is an important component because it is responsible for identifying user and also managing communication between clients. Without an efficient naming system, communication may become disorganized, especially when many users access the platform simultaneously. The naming mechanism is implemented using the naming system class where username and server location are stored in a hash map. This allows faster user lookup and efficient message routing between servers. Different naming approaches can be used in distributed systems, including flat naming and structured naming. Flat naming uses a simple username such as Aina and Dr. Shu, making it easier to implement. However, it becomes less efficient to manage as the number of users grows. In contrast, structured naming uses hierarchy usernames such as aina.chat.uni.edu and drshu.chat.uni.edu, which provide better organization and scalability. Therefore, structured naming is more suitable for systems that handle a large number of users. Based on the comparison, structured naming is more suitable because it provides better organization and scalability when managing a large number of users within a distributed environment.
First, this slide explains replication and consistency in distributed system. Replication means data is copied across multiple servers. This is important because it ensures availability and fault tolerance, meaning the system can still work even if one server fails. Next is eventual consistency. In this approach, data may be temporarily different between replicas. For example, replica A received the update first, while replica B received it later. However, after some time, all replicas will eventually become the same. Then we have sequential consistency. In this model, all updates follow the same order. The system uses synchronization, where only one thread can update at a time. This ensures the data is always accurate and consistent for all users. This slide explains how the system maintains reliability using replication mechanism. First is replica synchronization, where updates are shared between servers. They may be delays to simulate network latency, but eventually all replicas will have the same data. Next is node failure simulation. In this case, one server such as replica B is made unavailable. However, the system continues running using another server, which shows fault tolerance. The advantage of this approach include high availability, better reliability, and scalability for the system. However, there are also some limitations. For example, data may be temporarily inconsistent before synchronization completes. In addition, the system becomes more complex and synchronization may introduce some performance overhead.
Next, for prototype or simulation, I will explain the simulation components of our university communication system. First, the thread simulation uses multiple threads to simulate concurrent communication between users. Each user is represented by a client process thread, while synchronization ensure accurate message counting. Next, the naming system simulation resolve username and identity the correct server. This helps organize communication efficiently within the distributed system. The replication simulation demonstrates data synchronization between replica servers. Update may arrive at different times, but all replicas eventually contain the same data, demonstrating eventual consistency. So lastly, the simulation flow show how users communicate through multiple threads. Username are resolved and replicas synchronize updates while handling concurrency and not failures. Next, I will explain the sample outputs generated from the simulation. The process management output shows that multiple users can communicate simultaneously using multi-threading. Synchronization ensures that communication remains accurate and conflict-free. The naming system output demonstrates how usernames are resolved and mapped to correct server, allowing communication requests to be routed efficiently. For the replication output shows data synchronization between replica server. Although updates may arrive at different times, all replicas eventually store the same data, demonstrating eventual consistency. The high concurrency output tests the system under heavy user traffic. The results show that the system can efficiently support many users communicating at the same time. This output shows a node failure simulation. Even when replica B fails, the system continues operating using replica A, demonstrating fault tolerance and reliability.
This section presents the analysis report for the proposed university communication system. The analysis focuses on the design decision implemented in the system, including process management, naming mechanism, consistency models, and overall system performance. First, we compare thread-based and process-based execution. Based on the analysis, thread-based execution provide lower memory consumption, faster communication through shared memory, and higher scalability compared to process-based execution. Although synchronization is required to prevent risk condition, thread-based execution remains more suitable for the proper system because it supports multiple concurrent users efficiently while maintaining good performance. Therefore, thread-based design was selected as it offer better scalability, lower resource usage, and faster response times for real-time communication. Next, we compare flat naming and structure naming. Structure naming use a hierarchical format such as aina.chat.uni.edu, which improves system organization, reduce naming conflicts, and support efficient user lookup through the naming directory. Compared to flat naming, structure naming is more scalable and easier to manage in large distributed environments. Therefore, structure naming was chosen because it provides better reliability, uniqueness, and resource organization. For the third trade-off, we analyze sequential consistency and eventual consistency. Sequential consistency provides strong data correctness by ensuring that all operations occur in the same order across all nodes. However, this requires strict synchronization, which increase latency and reduce scalability. On the other hand, eventual consistency allows temporary inconsistency between replicas while ensuring that all replicas eventually reach the same state. As a result, eventual consistency was selected because it offers better availability, responsiveness, and scalability for real-time communication systems. Performance evaluation scenario. The system was also evaluated under several operation scenarios including high concurrency, replication, node failure, and naming resolution. The results show that the system remains stable when handling multiple concurrent users. Replication improves fault tolerance, naming resolution is performed efficiently, and services continue to operate even when replica nodes become unavailable. Overall, the system demonstrates good performance, reliability, scalability, and fault tolerance within a distributed environment. In conclusion, thread-based execution, structure naming, and eventual consistency are the most suitable design choice for the proposed university communication system because they provide an effective balance between performance, scalability, consistency, and reliability.
In conclusion, this project has effectively developed a distributed university communication system which employs process management, structure naming, and eventual consistency technique. Through simulation, it has been shown how several client threads and distributed nodes can effectively communicate using the developed architecture. By employing structure naming within the design, resource management was simplified along with service search capability. Additional, by implementing the eventual consistency technique, replicated data could efficiently synchronize within the nodes without having increased communication costs. Multithreading, on the other hand, facilitated efficiency processing of concurrent requests. Based on the analysis performed, it can be stated that the developed system is capable of performing efficiently even with delays in replication and concurrent processes. It must be noted that despite temporary stale data resulting from eventual consistency, the technique proved more scalable and faster than strong consistency technique. Through this project, valuable experience regarding the development of distributed computing system was gained.